Hello, students. Let's talk about significant figures. So someone asked, what are significant figures? Why should we care about significant figures? Well, anytime you're making a precise measurement, you want to make sure that you're communicating to the scientific community exactly what you actually measured. If you're going to put together an atomic bomb and you need to collaborate with another team, you need to make sure that both of you actually measured what you actually measured. And so your numbers should reflect that. So we're going to show how to utilize significant figures so that when you're talking scientist to scientist, you aren't lying. Because I don't want you to be science liars. Come on. All right. Significant figures help to define the precision of our measures and calculations. Because we're going to make calculations with these numbers too, guys, believe it or not. The last significant digit in any number is always the one we are least certain of. We're more certain to the left, we're least certain farthest to the right. The smallest number is going to be the least certain. So example, 10.00 grams. This is going to be our least certain digit because our tenths is the precision. That's how precise we were. And the instrument had the smallest marks of the tens place. Remember, we always estimate one more digit. This one, 10.0 grams, again, a very different number than 10.00 grams, suggests that the ones is our highest level of precision. This is our estimated digit. And it means the instrument had the smallest marks in the ones. And 10 point grams means that this one is the tens place is the highest precision, and the instrument only measured to the tens place. This is our estimated digit. So let's talk about these rules. I'm first going to go through the actual rules, and then I'm going to talk about how I, in particular, figure them out. So the first rules. All non-zero numbers are significant. So 7, 8, 9, 4, anytime you see one of those, that's a significant number. If you have two non-zeros, so if you had 104, this is significant. It's a significant zero because it's between two non-zero numbers. Zeros in front of non-zeros are not significant. So if we have 0.014, these are not significant. If we add one after this, it is. In fact, that is called a trailing zero. Sorry that this is difficult to see at this point. But that last zero, so if we have 0.120, both of these are significant. If a decimal is involved. Remember, only if a decimal is involved. So my preferred way to figure out whether things are significant or not is the dot move right, not move left rule. Remember, dot move right. We're going to start here. We're going to move right until we hit the first non-zero digit, which is our 4 here. And then we count everything else. This is significant, this is significant, this is significant. So again, this is the first non-zero digit. And that's what counts. Now, if you don't have a dot, you don't have a decimal, you move left. Meaning we got to start over here. So we're going to move here. We're going to go to the left until we hit our first non-zero digit, which is the 1, meaning the 1, the 5, the 0, and the 6 are all sig figs. Sig figs. All have 4 significant figures. So let's practice this. Oh. Special case. I want to talk about a special case. Exact values have unlimited number of significant digits, and we're going to get to a place where we're doing calculations with these, and you would think infinite sig figs, that's going to throw things off. It's really, you can just ignore them. But I'm going to tell you these special cases. Anytime we have count values, so the number of eggs in a carton, the number of students in a class, or the number of hydrogen atoms in H2O, we can count these. 12 eggs. There's always going to be exactly 12 eggs, but it's 12.000000000 eggs. Infinite number, unlimited number of significant digits. Students in a classroom, we know exactly the number in a given class. Period 6, 13 students, always going to be 13 students, so we know that is a count value. And also conversion factors. If I say 1 kilometer equals 1,000 meters, that means that there is 1.0000000 kilometers and 1,000.00000 meters. There's always an unlimited number of significant digits, so you don't count them. And when doing math operations, remember, ignore the unlimited sig figs. You just use the other ones that you go on. So how many sig figs? Let's do some practice. So this is right here. We see no decimal, so we're going to move right until we hit this first one here. We have 1 sig fig. How about here? Oh, there is a dot. Meaning we're going to start here, and we're going to hit that first one right away. That means this is significant, and this is significant. That's 3. What about this one? Again, here's our dot. So we're going to start here. 3 is our first non-zero digit. 1, 2, 3, 4, 5. 202 trees. Oh, well, we saw 10,000 centimeters, 10,000 meters, 10,000 grams. So it's just probably 3, right? Wrong. It's infinite because this is a count value. This is like students in a class. These are SI units. We're going to use these in measurements. Trees is not an SI unit. There's not 202 trees in a field of trees. That's not an SI unit. It's infinite number because it's a count value. 4.07 has 3. Again, we'd start over here. This has 4. Let's think about this. Okay. Remember, these non-zero or these leading zeros don't count. We would start over here. Nothing, nothing, nothing. First one, 9, is our first non-zero, so these 4 are significant. This is 3, same reason. Start here, move. This one, this one, this one is significant. 3. And this one is 4. Again, we don't start over here, we start here. 5 is our first non-zero digit. 1, 2, 3, and 4 sig figs. These are trailing zeros with a decimal. They are significant, but again, if you just remember a rule, dot, move right, not move left. This was our not. These all other ones had dots, so we were moving right. And finally, again, do we see a dot? Nope. So we're moving left. We're gonna go, 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 go until we hit that 2 right here. 1 sig fig. Scientific notation. Again, it's got the word scientific in it. It's probably important for science. There's a hint. It actually is. It makes life easier. You'll see it's even easier to enter things in your calculator once you get them into scientific notation. But that's getting ahead of myself a little bit. Let's talk about scientific notation. It's used to communicate really big guys, really small guys in terms of numbers. So you don't have to write out a bajillion zeros. For instance, this is a tiny little number here. 0.0000000000100 is actually 1 times 10 to the negative 9, and 13000000000 is actually 1.3 times 10 to the 9th. It makes life easier. Let's talk about where we got these from. So remember, scientific notation, you've done it before probably. It's going to be, the number out front is going to be a number between 1 and 10. Not actually 10, because that's 2 digits. It's just going to be 1 digit between 1 and 10, not 0. So we have 1, we have 1. We need to move the decimal to where it is going to give us that number. So to get to this negative ninth, we went from here 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces to the right. If you're moving to the right, then we are dealing with negative exponents. We're moving in the smaller direction, so it has to be negative. But if we're moving the opposite direction, where we're going in the bigger directions, we're going from hundreds to thousands to millions to billion, then this is going to be a bigger number. So let's count 1, 2, 3, 4, 5, 6, 7, 8, 9. Exactly. So it is 1.3 times 10 to the 9th. Well, wait a second. This one's got 2 zeros. We didn't even keep any of these zeros. Where'd that happen? Why is that the case? Well, remember, if we were figuring out the sig figs here, we would start here, because it's got a dot. We would move right. This is our first non-zero digit, but these are also significant digits. So we're going to keep them. However, there's no dot over here, so we're going to move to the left, and we're going to go until we hit this 3, and this is our first significant digit along with a 1, so these are the only two they're going to keep. Because in scientific notation, all numbers before times 10 to the whatevs are significant. All of them are significant. Those are the only ones that show up in scientific notation. Let's try a few. First, we'll do scientific notation. So, 93,000. Again, we're going to move to the left. 1, 2, 3, 4, 5, 6, 7. However, if we're moving to the left, we're getting bigger numbers. So this is 9.3 times 10 to the 7, which is going to show up over here. So let's get through all these. All right, like I said, there, 9.3 times 10 to the 7. Let's figure this one out. We want it, again, to be one digit in front, so we're going to move to the right. We're moving smaller, and we move 1, 2 times. That means it's going to be 1.0, remember this is significant, times 10 to the negative 2. All right, how about this one? How many sig figs first? We'll do it a slightly different way. Just 2, again. And we figure out 1, 2, 3. 1.7 times 10 to the 3rd. This is a small number, so we're thinking small numbers. We're going to have negative exponents. How many times? 1, 2, 3, 4. Absolutely. How many sig figs? These are just placeholder zeros, so they don't count. 2.546. Yeah, times 10 to the negative 4th, because again, we move to the right. How about this one, though? Oh, that's tricky. We're going to move this direction. However, let's move this direction. 1, can't stop here. 2, 3, 4, 5, 6, 7. Okay, and it's to the left. It's a bigger number, so it's going to be a positive 7, so we're times 10 to the 7th. But what? This 2's kind of wonky. Let's see. We move to the right. This is our first non-zero digit, so all of these are significant. That seems like, yeah, you got to show all the significant digits. Even if there's a whole bunch of zeros in there, you got to do it, because otherwise you're not accurately communicating how precise your measurements are. The whole point is sig figs. Let's go the opposite direction. We'll go sig, or scientific notation, the other direction, into standard form. So we've got times 10 to the 3rd. We know this is going to be a bigger number because it's a positive exponent. So we're going to move 1, 2, 3. We went under the 3, under the 6. Now we got to put a 0 in there. So 7360. How about this? This is a small number, So we're going to, instead of moving to the right like we did before, we're going to move to the left. Start with the decimal. 1, 2, 3, 4. This is under the 2, but these require zeros. And our decimal is going to be right here. So it should be 0.00025. Bam. 1.7 times 10 to the first. This should be an easy one. Again, we're going to be bigger. This is positive. Right. 1.7 times 10 to the first is really just 17. And again, remember, this is not a very large number, so this seems a little silly. But with bigger numbers, with smaller numbers, it is a little bit better to use. How about this one? 1.234 times 10 to the negative first. Which direction are we going to move? This way, right? No, it's a negative exponent. Come on. We're going to move this way, not this way. So we have 0.1234. How about this number? How fun is this, huh? Times 10 to the 23rd. So we know this is going to be a big number, right? So let's figure it out. 1, 2. All right, I only need to move 21 more times. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Hey, all right. So what's that number look like? Yeah, this. 602, 000, 000, 000, 000, 000, 000, yeah. 602 sextillion. Absolutely. That is Avogadro's number. We're going to see it later. Avogadro. Wow, that's great spelling. Avogadro's number, which is our next unit, guys. We're going to talk about the mole. I know you're excited. And why wouldn't you be? All right. I thought that was really helpful for me to review. I hope it was great for you to learn this material. Scientific notation, sig figs, super important to use when you're communicating with science because scientists care about numbers, guys. They matter. I hope that was helpful. Expecto Patronum!